Welcome back to our second segment of lesson 3, where we will be looking at derived units and quantities. And we'll be taking some classwork. Okay. In lesson 1, if you remember, we gave the overview of derived quantities. From the word derive, you derive them, isn't it? Just like, area, length times breadth, okay? Which gives the unit. Length is in meter, or it's a distance. Breadth is also another length, isn't it? So together you have m times m giving m squared, correct? And then volume, you have 3 linear dimensions, isn't it? You have length, breadth, and height, okay? M times m times m, okay? Giving m cubed. This is a power, okay? Not m2, okay? It's m to the power of 2, okay? That is how it's written correctly. It is a mistake here. So it's m squared, m cubed, okay? Then you have density, which is mass per unit volume, okay? Density mass per unit volume. So density raw mass over volume. Okay, so mass is in kilogram, the SI unit. Volume is in meter cubed, isn't it? So given the unit kilogram, when it comes up, minus 3 from indices, isn't it? Correct? So this is derived from two quantities, isn't it? Mass and volume. Then you have velocity, which is displacement per unit time. Displacement is that's distance or length, isn't it? Time is in seconds, so meter per second. Acceleration, which is change in velocity per unit time, meter per second squared. Because you have, in the case of acceleration, you have velocity per unit time. Velocity is in meter per second, then divided by another second. Okay, from mathematics, it will tell you that this will change. This is meter per second, then times this second will go down and multiply with this one. Okay, meter per second, then divided by second. This second will go and multiply this one, so it will become meter per second squared. Okay, what about, just out of curiosity, what about if it were the other way around? If it, let me say second on top, second divided by meter per second, how is it going to be? This second will go up now and multiply this one. Yeah, so it will now become second square per meter. Okay, it will now become second square per meter. Okay, so it depends on where the fraction is. Okay, this one. Okay, is it as a numerator or denominator? If it's denominator, then it will go down and multiply the, if it's numerator, to the denominator of the first fraction will multiply the denominator of the second fraction. If it's the other way around, then it will go up. Okay, it will go up. But simply going up is simply changing, like in this case, we're simply changing division with multiplication. Okay, because like now, this is meter per second, then divide by second. Okay, meter per second divided by second. So when we change this sign to multiplication, we invert this one, so it becomes meter per second times 1 over second. So that's why you have meter per second squared. Then in this case, you have second divided by 1, then divided by meter per second, isn't it? When you change this division sign to multiplication, you invert the fraction. Okay, so you have second times now second per meter. Okay, you invert this fraction, so this one becomes second square per meter. Well, this is some simple mathematical manipulations that although simple, but I tell you, some may find it new. Okay, so these are all derived quantities. Okay, why do we call they are derived from some fundamental quantities? Basically, sometimes you can have derived quantity being derived from a fundamental and another derived quantity, or derived basically from fundamental quantities. Okay, in the case of area, you have fundamental quantities. In the case of acceleration, you have derived quantity and a fundamental quantity. Velocity is a what? Derived quantity, isn't it? Time is a what? Fundamental quantity, isn't it? So then acceleration is a derived quantity. Is that clear? So derived units, and so these are other derived quantities. You have force, force, mass times acceleration from the second Newton's law of motion, which is the definition of Newton. Okay, then Newton, meaning is both. It can be written as a derived quantity and as a spatial unit, because you have quantities, mass and acceleration, isn't it? So Newton, even though we use spatial unit for it, but it is a derived quantity. Okay, but what that means is that Newton can also be written in form of its derived quantities, isn't it? It can be written in, because Newton, F equal MA. M is in what? Kilogram, the SI unit. A is acceleration, meter per second squared, right? So this is what? Kilogram meter per second squared, okay? And this is given a spatial unit called Newton, isn't it? Just like pressure, which is force over area, the unit, you see, Newton per meter square or Pascal. Pascal is the spatial unit for pressure. But the derived unit for pressure is what? Newton per meter square. Is that clear? So it can, you can, though hardly do you see force being represented with kilogram per meter square, but pressure, you can see pressure written in Pascal as well as Newton per meter square. Okay, the Pascal is the spatial unit. The Newton per meter square is now the derived unit. Okay, but pressure is a derived quantity. Whether you use Pascal to represent it or Newton per meter square, the same thing as force is a derived quantity. Whether you use Newton to represent it or kilogram meter per second square, it is a derived quantity. Clear? You have momentum, mass times velocity, work, or energy, force times distance, and work, power, work over time, which is watt. Okay? Meaning, because power, starting with energy, force times distance, it can be represented with joule or Newton meter. Okay, so energy or work can be represented in two ways, either joule or Newton meter, and both are used. Okay, both are used. Okay, to represent energy or work, joule or Newton meter. Then power, joule per second or watt. Usually watt is used, but sometimes you can see joule per second. Okay, they mean this. I mean, they all represent power, and they are all derived quantities. Okay, you have momentum, mass times velocity. You see kilogram meter per second squared or Newton second. The two units can be used to represent momentum. Kilogram Newton meter per second is kilogram mass, velocity meter per second, isn't it? So together you have kilogram meter per second as the unit for momentum, or Newton second. Force is Newton. It's not because from the Newton second law, this one can be changed into change in velocity per time. Okay, and momentum is mass times velocity, which is this one. Did you see it? Okay, that, and then so when you have mass times the change in velocity equal ft, this is called impulse, ft. Okay, this one in the laws of motion, you might have done it, which we are going to do later. It's called impulse. Okay, and this is called momentum. They have the same unit. So whether you choose to use the unit here, which is kilogram times the unit of velocity meter per second, or the unit of on the other side, which is Newton times time, isn't it? Unit of ns. So whichever one can be used to represent momentum. Clear? And both are derived quantities. Okay, you have frequency f, number of oscillations per second. Number of oscillation is unitless, isn't it? It's just a number without any unit. So you have it per second, but hertz is used to represent that, okay, as frequency, which is a spatial unit, okay, but it is a derived quantity, frequency, number of oscillation per second. Clear? You have a question? Okay, go ahead.
What is number of oscillation?
Number of oscillation, the number of times something oscillates.
Times.
Yeah, the number of times. Number is just a number. It's like number of revolution, number of rotation. Okay, when you have, let's say, a simple pendulum, it oscillates, isn't it? Okay, between two extremes, right? It goes one, let's say, a complete rotation. Okay, one oscillation, two, three, or depending on the way you count it, isn't it? So it's just a number. It's like just simply the number of times something rotates. Okay, one, two, three. So oscillate, oscillations. Okay, just like in the case of simple pendulum. Clear? So it's simple, is simply a number, okay, which is unitless. Clear? Can we go ahead? Good. Now, quiz. Yeah, this will test your understanding, you know, of these simple concepts. Okay. Oh. The first one says, which of the following are fundamental units? Okay, which of the following are fundamental units? So A, kilogram, B, kilogram per meter cube, C, second, D, meter cube, E, Newton per meter cube. Which of them are fundamental units? So raise up your hand and then who can answer this? Want to answer? Okay, Aline, go ahead.
Can the answers be more than one?
No, this is A, B, C, D. So there is only one unique answer. Which of them are fundamental units?
A.
Yes, here answer can be more than one.
A.
You're right. Answer can be more than one in this case. Okay, so it's not a unique single answer. Okay, so there can be more than one. So what are the answers?
A and C.
A and C. That is kilogram and second. Okay, so A and C are fundamental units. Correct? So let's move to the second question. Which of the following units, which of the units of the following physical quantities are derived? Which of the units of the following physical quantities are derived? So you have physical quantities. So which of them have derived units? Do you understand? You have area, thrust, pressure, mass. Which of their units have derived, which of their units are derived?
Both of them are only one.
No, I don't know. Not only one. You can have more than one. You see, this is SSE. This is SSE question, okay? I don't know, maybe WIEC or so, but just written as SSCE. Okay. So, which of them?
Please, what is the meaning of thrust?
What?
Thrust.
Thrust? Thrust is a force. It's a force exerted.
Okay, so it is 1, 2, and 3.
But thrust is a type of force. Okay? So, which of them have derived units? 1, 2, and 3?
Yes.
Okay, yes, correct. Area is a derived quantity. M times M. Thrust is a force. M times acceleration. Pressure, force per unit area. Mass is a fundamental quantity, isn't it? It's the only one that is not that does not have a derived unit. Now, how many seconds are there in one day? In a day, year, and month of March? How many seconds are there? This you will have to work it out, right? You'll have to work it out. How many seconds are there? 1 year, 2 day, 3 months of month of March. You have to work it out. Are you done? Done? Okay. This question is simply asking you to convert year, day, and month of March into seconds. Simple. Okay? And in our previous class, we did conversion of units, isn't it? So, what is the answer? Let's start with year. Okay? Year. Okay? How many seconds are there in a year? Okay? So, are you done? Year, 2 day, and then 3 month of March. Okay? Finish? Okay. Come and give me that of here. Ayoma, want to solve it? It's a very simple question. Yet, like I said, you need to understand conversions of unit. Okay? Yeah. How many seconds are in a year?
First, we are going to
Okay.
in an hour.
I'll just plug it here. Clip it, yes.
In an hour, there are 3,600 seconds.
3,000?
600 seconds.
How? How do you know that?
Okay.
Yeah, take us through.
There are 60 seconds in a minute. So
Okay. 60 seconds, 1 minute. Yes, this we know. No, this is not M. Minute is not represented with M. Oh, good, good.
Then there are 60 minutes in an hour. So we are looking for how many?
60 minutes in 1 hour? Yes.
So we are 60. But we do not know how many
minutes in 1 hour?
Yes. But we do not know how many seconds are there in a minute.
Okay.
60 minutes. So we are
Okay.
looking for that. You represent it as X.
Okay.
So you cross multiply.
Okay.
And
So X equals 60 by 60. Which gives what?
3,600
seconds in 1 hour. Good. Yes.
So therefore, in 1 hour we get 3,600 seconds.
When writing numbers, do not use comma. We use comma when writing money, okay? But usually when writing digits, when doing your calculations, don't separate the thousands with a comma, okay? Just write them, okay? Yes.
So in 1 hour we have 3,600 seconds.
Yes.
So in a day there are 24 hours.
Okay. In a day.
Yes.
So how many seconds are there in that case?
Since we said 1 hour is equals to 3,600 seconds.
So
and now there are 24 hours in a day.
Yes.
So 24 hours. We do not know how many seconds are there in 24 hours. So
X, okay.
Cross multiply.
Okay.
X is equals to 3,600 times 24.
Okay. Which gives, what do we have?
6,400.
Okay. Okay. It's 6,400. Yeah, seconds. Good.
So So in 24 hours, it's 6,400 seconds.
Okay.
Then
So this is in 1 day.
yes,
Now in 1 year.
in 365 days.
Days. Perhaps 365 days in a year.
400 seconds.
No, this is in one day. Right?
Yes.
Yeah, this is in 1 day. 1 day contains 8,000, yes. 8,000, it's 6,400, yes.
So
In 1 year,
yes.
365 days. How many seconds are there?
Looking for
X.
that.
Okay.
We cross multiply. X is equals to 86,000. It's 6,400 times
365. So what is that?
That's 1. No, that's 1 million.
That's 1 million. 536,000.
Thousand.
Okay. No. 3 zeros. Seconds. So this is the number of seconds
For
in 1 year.
1 year. There are 31,536,000 seconds.
So in scientific notation, like I said, we don't use comma, but to reduce like big number, we simply write it maybe in exponential form. Maybe 3.1536 times 10 to the power of what? We're saying million, isn't it? We're saying million. This is 3. Seven. Good. Seconds. All right. Excellent. So, you see, this is a simple conversion, okay? But I tell you, if you don't know it correctly, I mean, it can land you in trouble, okay? In some calculations. Now, the next one, day. How many seconds in a day? Hello?
How many seconds in a day?
Yes.
It's 6,000.
Yeah, because it's already calculated, isn't it? So, 1 day, which is 24 hours, we already have the answer here, isn't it? Okay? So, 86,400. Then the next one, the month of March. So, the first question is what? Huh? The first question that will come to your mind is what? When you are asked to, how many days are in March? Good. So, how many days are in March? 31. Oh, so you either memorize it or you have to go to your calendar and check. Okay. Some are taught the number of days in a month right from primary school, right? So you should remember that during our days we don't have that that song. Okay. So up till now, I don't know the number of days in. I only remember that of February. Is it 28 or 29? Because it depends. You can have a leap year, but apart from February and some few months, I don't know for all the months. So March is 31 days, right? So since we said 1 day is this, so for 31 days will be 31 times this, isn't it? Correct? Which will be what? So March 2 million 678 400. So times 10 to the power of 6. Okay, since it is 2 million. Okay, this is S second, or I can make it to two significant figures, maybe 2.7 times 10 to the power of, no, the same 6 seconds. I didn't move the decimal point. Okay, so if I had moved it, that is when the exponent will change. Clear? So we are done with this question, right? Can I clean the board? Okay. All right, let's move on to the next question. Distinguish between fundamental and derived units and derived quantities. Give two examples of each. So one of you should distinguish between fundamental and derived quantities, and then one of you should give me two examples of each. So who is starting? Distinguish. What is the difference between them? Simple. Hello. Between fundamental and derived quantities. Okay. Marioma.
Derived quantities are subsets. It's a subset of fundamental quantity. Yeah. Derived quantities is made up of two or more fundamental quantities.
Good. Good. So fundamental quantities is a subset of derived quantities, or what? Or is, well, let's just put it, derived quantities are made up of fundamental quantities. Simple. Or at least one or more. Okay? One or more. Because a derived quantity can be made of another derived quantity and a fundamental quantity, isn't it? We have seen in the case of acceleration, isn't it? But fundamentally, a derived quantity is made of fundamental quantities. Okay? Simple. Now, give two examples of each. Two examples of fundamental quantities.
Fundamental quantities.
Yes.
Mass,
Yes. No, unit. Yeah, quantities. Okay, quantities.
temperature.
Mass, temperature. Yes. Two examples of derived quantities. You want to answer? Okay, good.
Area and volume.
Area and volume. Good. So they are both examples of derived quantities. Excellent. Now another quiz. Okay. The internationally agreed system of units, SI, for physical measurements are A, B, C, D. This is a jump question. You can see that. Okay? So, what is the answer? A, B, C, or D?
C.
C. What is C? Kilogram meter second. Okay. So, the internationally agreed system of units, SI, for physical quantities. Yeah. The answer is C, isn't it? Which is the three basic fundamental units, isn't it? Kilogram meter second. Okay. Others you can see centimeter, gram, second. Okay. Kilogram, second, and centimeter. Centimeter is not SI unit, isn't it? Then the next one, which of the following is not a fundamental SI unit? Which of the following is not a fundamental SI unit? This is another jump question. You see, you have started answering jump questions, right? In SS1. It goes to tell you, you know, even when you go reach SS3, the questions are going to be cumulative, isn't it? You are not going to be examining only on what you did in SS3. It has to start from SS1, isn't it? Okay? So anything you learn from SS1 up till SS3, you have to learn it very well and understand it. Okay? So what is the answer here?
E, radian.
Radian? Okay. So which of it is not a fundamental? Yes, radian is not a fundamental unit. Radian, by the way, do you know what unit? Oh, radian is the unit of angle. There is the SI unit of angle. Okay, rad. It's written as rad, R-A-D. Okay, unit of angle. You can use degree, isn't it? 180 degree is equal to, I think, 1 rad equal 180 degree or so. 1 rad. So radian is the SI unit of angle. Okay? No, I think 180 degree over pi. I think that is pi. Okay? But usually you use radian in further math. Okay? In general math, hardly you just stick to degree and that suffices. Okay? But it's the SI unit of angle. Which of the following is a fundamental unit? Another jump question.
D.
Good. Fundamental unit D. What about A, B, and C? What are they? What are they? A, B, C. What are they?
They are derived.
They are derived. Newton, unit of force. Watt, unit of power. Joule, unit of energy, isn't it? Or work. So they are, the remaining are all derived, while only D is a fundamental unit. Did you see, these simple questions? This is from JAM, isn't it? But if you don't understand them, no matter how simple they appear, if you don't know them, you are bound to miss, isn't it? Because making educated guess here and get the right question, I mean, the probability is very low, right? Now, another quiz. Okay, now, this is more, not complicated. What are the SI units of K? So that the equation, velocity equal Kx, K times density, is dimensionally correct. Give your answer in terms of the basic units. So let me explain this question in clearer terms. We want to find the unit of x. Like, let's say in this, suppose you have F equal Ka, where K is a constant. Okay? We want to find the unit of A. This is force, this is acceleration. How do we find the unit of K?
Over K.
Over A over A. K is equal to F over A.
Good. K equal F over A, isn't it? And then, what is the unit of F? And isn't it unit of A, meter per second squared, right?
Yes.
Okay? And then, so K is going to be Newton second, because the S will go up, right? Newton second per meter. Okay? Correct?
Yes.
Although if we put Newton here, this will simplify to give us kilogram. Let's quickly do it. What is Newton? Kilogram, meter per second squared, isn't it? This is Newton times Newton second per meter. So simple indices, right? So we have kilogram, meter, and then this is meter, this is per meter. It's going to cancel, right? Okay. Then this is per second squared, and this is second. Oh, sorry. This is second squared. This is squared, isn't it? Because this acceleration. So per second squared and second squared. Minus 2 plus 2. S power of 0. S power of 0 is what? 1. So what do you end up with? Kilogram, right? Correct? So I'm just giving you so that you understand this question clearly. Now solve this one. Velocity equal K times density. You know what is velocity, the unit of velocity, right? You know what is density and the unit of density, correct? Correct?
Yes.
And then what is the unit of K? Work it out in similar fashion as we have worked this F equal Ka. Okay? So that's why, I said classwork. This one you'll have to work it out here. Okay? And it tests the basic ideas that we have introduced. Done? You're not writing anything? Finished? So, what is the problem? Did you understand this one?
Yes.
F equal Ka. K, we want to find the unit of K. We know that of F and A, isn't it? Apply the same principle. The same principle. Of course, the unit of K in the question here is going to be different, okay? But the steps are similar. So F equal K times density. What is the unit of density? What is the unit of velocity? Simple. Substitute them and make K the subject of the formula. Simple. Do you understand? Okay. Done? Hello? Not yet? I told you. What is the unit of velocity? Okay. What is the unit of density?
Kilogram meter.
No, kilogram per meter cubed. So substitute their units and make K the subject. Clear? Yes, yes. Mariam. Are you done? Okay. Hello. Done?
You got kilogram meter per meter squared seconds.
You got what?
Kilogram per meter squared second.
Okay, let me erase the board and write your answer, and then we'll work out the solution together. What did you get? You got kilogram per meter cubed, so meter to the power of -3 seconds here. Okay, per meter squared, then seconds. You got this? Hello? Why are you not done yet? Okay. So this is Mariam's answer. How many seconds shall we give you to finish? How many seconds? Okay, we can go to the next question before you finish. Which of the following is a fundamental quantity? Heat capacity, electric current, torque, reactance, density.
B.
B, electric current is a fundamental quantity. Yes, that is correct. The other quantities, they are all derived quantities. Okay, done? What is the answer?
Kilogram
Square.
Per second. So kilogram per meter square per second. Okay. Now, this is Halum's answer. Now, let's work it out and see, because the two answers are different. Let's see if to see which one is correct, because definitely all cannot be correct. So let's work it out. It says velocity equal K times density, right? Okay, so just like we mentioned, you simply make K the subject of the formula. So this is velocity over density, correct? By dividing both sides with density. So, and then we plug in their units, isn't it? Velocity is in meter per second. Density is in what? Kilogram per meter cubed. Now we have this multiplication. Let's change it so that we multiply clearly. So this is meter per second. Changing the division sign to multiplication sign, we invert the denominator, isn't it? We invert it, correct? So it becomes meter cubed per kilogram, right? Correct? So now, what do we have here? Okay, we have kilogram as a denominator, isn't it? So per kilogram, right? Per kilogram, and then meter here, m times meter cubed. What do we have? Meter to m to power of 4, and then per what? So this is the unit of x, right? So which one is correct? Kilogram, kilogram. No. because it is per kilogram, meter to the power of 4. This is per meter square, this is per meter square. No. Per second, yes, no. Do you understand? Is that clear? Alternatively, you can simply plug in the unit here and the unit here and then make K the subject. Simple. Okay? Now, we have other questions. Which of the following is a fundamental quantity? Dude, yeah, I should be asking you this. Which of the
C.
following is a fundamental quantity?
C.
C, length. Yes. Others are derived quantities. Okay? I mentioned about impulse, isn't it? First times time. Which of the following is a derived unit? Good. Which of the following is a derived unit? Anyone?
D. Ohms.
D. Ohm. Okay. So ampere, second, Kelvin, and kilogram, they are all fundamental units. And ohm, which is the unit of resistance, isn't it? Okay. Unit of resistance. In electricity, you will learn about resistance. Okay. From volts equal V equal IR. Okay. Voltage, it's called the current times the resistance. Okay, so it's the voltage over the current, which is given a special unit. Ohm is a special unit. Okay, it has a derived unit. Okay, which is volt per unit current. Okay, so this is in electricity. Just trying to say that ohm, although it's a special unit, but it is a derived unit. Okay, now you need to work this out. Okay, it says a sphere of radius r moving with a velocity v under streamline conditions in a viscous fluid experiences a retarding force F. Don't worry about the long description given by F equal KRV, where K is a constant. Simple. So F equal KRV, just like we did F equal KA, isn't it? So here R is radius, V is what? Velocity. Now, derive the SI units of K in terms of the base units. Okay? In terms of the base units. And the base units here refers to the fundamental units. Okay? The very base, the fundamental units. Okay? So meaning, so F equal K RV. You know the units of all the quantities except one, isn't it? K. Find the unit, the SI unit of K. Okay? You have 2 minutes to work it out. Two minutes to work it out. F equal KRV. KRV. Okay? What is the answer? And this is the last question, by the way. So that's why, the last one is the toughest. R is radius, V is velocity. You know the units of all the quantities involved, right? You know the units of all the quantities involved. Okay. Hello. You know all the units, right? Except K. Good. So that makes it easier. Doge is not working it out. Alum done. Okay. Done? Good.
kg per second.
What? Kilogram per second. Okay. So this is Mariam's answer. Hello.
Kilogram meters cube per second.
Kilogram meters cubed per second cubed. This is hello. Right? Now, let me work out my own and see which one is correct. Okay? So, I will approach it differently. I will just insert the units, okay, of the quantities. First is Newton, because it says in terms of the base units. So the base units are the fundamental units, right? So Newton is kilogram meter per second squared, right? Kilogram meter over second squared, correct? This is force. This is equal to K. R is radius. Unit of radius is what? M, isn't it? Because it is length. So M. Velocity is what? Mariam? The unit of velocity, SI unit of velocity. Okay. So meter per second. Okay. So all I need to do is to make K the subject of the formula, right? Before I do that, I can strike out M, isn't it? From both sides. So I take M per second to the other side. And then because it crosses the equality sign, I invert it, isn't it? So K is now equal to kilogram per second squared. When I change M over second to the other side, it becomes second over M, right? And then from here, S will cancel one here. And what do I have left? I have kilogram, okay? I have per meter, this one. Then I have what? Per second. So let me see. Kilogram, yes, both of you. Then per meter, no, this one, there is no per meter. This one is meter cubed. And then per second, yes, this one, second cubed. Did you see why we made mistakes? Okay? So the actual unit is kilogram per meter per second. Clear? Now, this has brought us to the end of today's lesson, and these are the references. These questions, all the questions were extracted from this book, New School Physics for Senior Secondary School by M.W. Anyakoha, 2016. Okay, you have copies. Okay, and then I also use other references. This is a Nigerian curriculum. This book is based on Nigerian curriculum, the first one. But then I went and looked for 2 American textbooks for high school physics. Okay, there's one conceptual physics, the high school conceptual physics, the high school physics school, the high school physics program 2009. Okay, and there is another one, must know high school physics. Okay, these 2 are all from American authors. Okay, using the American system. Okay, why do I use these 2 books? Because the American system of education, to say the least, is the best you can have. Okay, and there are books in areas. When you find good books written by American authors, you realize that they are very excellent in such areas. But I cannot just pick the American books and use it as the main reference, because we have our curriculum, the Nigerian curriculum. So the first one is written purely using the Nigerian curriculum, which will enable you treat all the topics required of you to sit for WAEC and NECO exams, okay, at the end of SS3, okay, and everything that is expected to know. But then these 2 will introduce you to the basic concepts in the areas. Like this one, the conceptual physics, there may not be numerous calculations, okay? Very few calculations, but it will explain the concepts very well, very well. It will explain the physics concepts in a way that will connect, it will connect with practical examples and all that. One of the comments I read when I posted the video online on YouTube, someone said the first lesson that when I explained the speed with which the earth moves, about 2.1 million kilometers per hour, you know, and how incredible that was. So he was saying, didn't I go too deep? And I I actually thought I went too deep until I started, reading the introductory chapter of this book, The Conceptual Physics. The first chapter, it started with this about science. The big idea. Science is the study of nature's rules. Oh, it's not showing. Let me quickly duplicate the screen so that it will show exactly what I have. All right. So, so it was explaining at the very beginning what would it be like to live in outer space. That is the first sentence. What would it be like to live in outer space? At first thought, we might think this question is for astronauts, and then he went further and further explaining, and trying to spark the interest of readers at the very beginning. You see, the study of nature's rules is what this book is about. These rules in physics are surprisingly few in number, explaining such things as why Earth is round, why its rainbows are colorful, arcs, and why skies are blue and sunsets are red. Understanding nature's rules adds richness to the way we see our world. These are some of the questions that during sunset it's red or amber, deep amber, isn't it? When it is middle, when the sun is, in the meridian, it is blue, isn't it? Why? All these are physics principles. Okay? So when I saw this, I said, then definitely, sparking your interest in the first lesson, explaining or giving you, touching on some deeper concepts and, talking about them, I wasn't going too deep because I wasn't telling you to understand clearly 100%, but just to spark interest, to make you understand, the overview of what physics is all about. Okay, so the conceptual physics is very important, very good. Okay, it breaks down the physics concepts for you to understand it with excellent applications. Okay, so you all have the books. Okay, I have already uploaded them. Okay, and yes, so summary, today we have looked, in details about, into units, the different systems. Okay, metric system, English system, the history behind them, the inch, the pounds, the cubit, the mile, the acre, the yard, and then how the metric system came about, as well as how the SI system now make it much, much simpler, giving the units in decimal forms, isn't it? Or connecting them using decimals, okay, and powers of 10, okay? And then we look at derived units and took some examples and exercises from the book, okay? So any question before we call it a day? In our lesson 4, we will go into measurements. Okay, we'll start looking into measurements. Okay, and that will be in lesson 4. So thank you and see you next time.